Hi guys, today we're going to be talking about chapter 4.3 and the part of it being definite integrals, as obviously founded by Newton and Leibniz. Um, and we're going to be talking about evaluating it as a limit and its definition, and as far as the properties of such definite integrals go. So first, let's start with the definition of definite integrals. And according to the textbook, a definite integral is equal to the limit as delta goes to 0 of the sum of, actually it's just a Riemann sum, so I don't really have to say that all. So it's a Riemann sum, the limit of a Riemann sum, sorry. This is equal to the integral as a goes to b of f of x times d of x. So this is the definition of a definite integral. And this is a being the lower limit of integration and b being the upper limit. And as far as proving that this is true, it has to be continuous on a to b for the function to be integrable on a to b. So therefore saying that continuity implies integrability. And so then this exists. Use that definition to evaluate a definite integral. So let's start with the integral, the definite integral as from -1 to 2 of x squared dx. Okay, so it's integrable on that function because it's, the function is integrable on that interval because from -1 to 2, so -1 to 2, it's just continuous. And by this definition, we're going to use the limit as this goes to 0 of the Riemann sum. So n being, let's say it gives us, or we don't know what n is, so it's on, we don't know the subintervals, which is n, and I being 1, as always, by the definition. So using this, we don't know what c sub I is yet, and we don't know what the change in x is either. So finding the change in x first, before c sub I, change in x equals b minus a over n, by, as we know that now, which is 2 minus -1 over n, so it's 3 over n. So now we're going to find c sub I, which is a plus change in x, or sorry, change in x times I. And since a is -1, it's going to be -1 plus 3i over n. And so now we're going to use that. So the function evaluated, you have to plug this into the function. So this right here, this integral equals the limit It's going to get a little redundant, but that's okay. It goes to 0 of n I equals 1. So you have to state the definition first. And then you can plug in everything. Sorry, substitute in everything. Into infinity. So we don't know what n is. I equals 1 of, okay, so it's 3i over n minus 1 squared times, and our change in x is 3 over n. So we're going to move this to the outside of the, not the limit, but the sum. So 3n times the sum and we're going to factor this out, FOIL this out. It'll be 9i squared over n squared minus 6i over n, and then plus 1. So we're going to factor out the n's now, or as many as we can actually. We can't factor out anything because of that one constant, so as I goes to n, so we're going to plug in the I squared. So we have this I squared right here, so it's going to be 9 times 9 times n times n plus 1. Sorry. Yeah, 9 times n plus 1 times 2n plus 1 times n over n squared, and don't forget the 6. 3 over 2, 1. Okay, and then this one becomes 6 times n plus 1 over 2n. So the n's cancel out, changes to 3. And then the 1 just becomes n. So this looks a little messy right now, but we'll fix it out. Limit as n goes to infinity of, okay, so 3 over n, sorry, times 3 halves, I'm just going to write it like that, 3n plus 1 3n plus 1, 3 times n plus 1 times 2n plus 1. 3 times n plus 1 times 2n plus 1 over 2n, and then minus 3n plus 1 plus n. I'm just going to get tight. plus n. So so whenever you would evaluate 3 over n at each of these, you have n squared on top, n squared on the bottom. You got 3, so it's going to be, this one's going to be 9/2, because as n goes to infinity, so the ratio of degrees is equal. So this one's going to cancel out to 9/2 if you were to multiply that times 3 over n. And then the next one, 3 times n plus 1 times 3 over n, is going to be the same degree as well. So it's going to be 9, because it's the leading coefficient is 9 over 1. So 9/2 minus 9. And then plus n. So the n's cancel out. It's going to be the limit is the n's cancel out, and that just becomes 3. So it's 4/2 minus 18/2, negative 4/2 plus 3 equals that equals negative 3/2, because this is 6/2. There are other applications to the definite integral. You can say already that the area is the definite integral of from a to b of f of x times a d of x, or dx, because all an integral is the area under a curve. So obviously a definite integral is going to be this that area specified. So we can use we can also use the properties of definite integrals to evaluate such definite integrals that we might look challenging at first. So like if x equals a, or if the function is defined at x equals a from a to a, so at the same spot on a function, no matter what function it is, at just that a of the function, the integral is just going to be 0, because there's no area to under the curve at just being at a. There's that one, and there's also yielding to whether or not it's integrable from b to a. So that's the opposite of the normal integration form of the function, would be just the negative of the normal integral function. So we can use this to evaluate from pi over 2 to pi over 2 of cosine of x, the integral from pi over 2 to pi over 2 of cosine of x dx, using the first property, that's just going to be 0. You don't have to do anything with it. You know for sure that that's 0. let's say from 4 to 2 of 3 plus, or sorry, x plus 3 dx. So you know that on a positive function like this, if it's going from 4 to 2, that's the opposite direction from the positive function. So this is going to be, that would be b and this would be a. So we know that that's equal to the negative of 2 to 4 for x plus 3 dx. And that is just simply 4 plus 3, sorry, yeah, and using a little math, we find that that equals it equals -2. So it's very important to remember those properties. And in addition to that, there's also the additive property, being the integral from a to b of f of x dx equals the a to c of f of x dx plus c to b f of x dx. And you can use this in any problem. In den Worten des Leibniz, auf Wiedersehen, meine Freunde. In other words, guys, see you next time.